Right. Good morning, everybody. Let me upload this document. Let's see. All right. So I just uploaded a document to the chat. That's the last handout actually for the semester. We only got today, Friday, and Monday. And those of you who have applied for graduation, let me put my number in here. I need to know who you are. I should have asked this sooner, but it's okay. Just text me at some point later today. Let me know and just put that you are in this class, CHEM 32101. So I think senior finals start. I think they might start today. Today through the 25th. So just let me know so I can set everything up, and then we'll have a discussion about that. For everybody else, on tomorrow, you can reach out if you want to inquire about your average or whatever. You can reach out on tomorrow. I have everything calculated up until if anything was submitted after the break, it's not included, but I can do that. I can pull that in too. But I have everything calculated up to the break. All right, let's go ahead and let me go ahead and share my screen right quick. We'll jump in and get started. And let's see. So yeah, go ahead and grab that handout out of the chat so you can have it. It's also on Blackboard. It's in a folder labeled final reactions, and you can get it there. But I also uploaded it to the chat. So we're basically going to talk about, and I have a video for this. I just didn't send it. I'll send it out today as reinforcement. But we're basically going to talk about from here four different types of reactions, right? So it looks like a lot, but it's really reactions of alcohols, conversions of alcohols into carbonyls, carbonyl reactions, and then amine reactions. So it's really just four classes. And this is only a smidgen, like the tip of the iceberg of what's actually, what we could delve into, but we just don't have time to do it. So I'm gonna try to truncate it so that we can just hit the high points. And normally I would go through all the mechanisms for these reactions, but I'm not going to do that for each and every reaction. All right. So for the alcohol reactions up top, once we see the one mechanism, then that mechanism is going to be applicable to the other reaction as well. So it's really the same set of arrows. It's the same with the carbonyl reactions. We're going to go through the mechanism for the Vidic reaction, and then the hemiacetal and acetal. We'll we'll go through that, and then we'll do the hemiacetal, and then from there you'll be able to like extrapolate from that what the mechanism is for the acetal. And the same thing with the amine formation. We're going to go through the mechanism for that as well. All right. And then we have a bunch of examples in here. Obviously, we won't have time to touch every example, but we will look at some selected ones, and yeah, and we'll go through it like that. All right. So let's jump in and look at this first set of reactions. Let me add a page. And I know this is like really crunch time. So it's crunch time for everybody. So So let me grab this set of reactions right here. I'm just going to copy them and paste them. Ready, paste. All right, so let's look at the first reaction here. And it's really, all of these reactions are going to follow the same basic mechanism. All right, so that first reaction is what we call transistor esterification or ester synthesis. And again, a lot of this is going to be predicated on your knowledge of functional groups, which should, again, carry over from part one, right? So we talked about all the different types of functional groups. So here you're trying to make an ester, and what you start out with is an alcohol and a carboxylic acid, right? So those two things together in the presence of an acid catalyst with heat, right? So let me just, so here's my, we'll go through the mechanism right quick. And at this point, everything now is nucleophile, electrophile chemistry. Right? All these mechanisms that we're going to be seeing is just identifying the nucleophile and the electrophile in each step and figuring out where the arrows go. Right. So here's my acid here. Right. And I'm going to, again, it says in the presence of an acid catalyst. Usually it's a strong acid like sulfuric acid, maybe a drop or two of sulfuric acid. But the acid is catalytic, right? So that means it doesn't react. It's only there to facilitate the addition to the carbonyl. So we'll say that the acid right, it activates the carbonyl. Right. So basically what happens in this case is the carbonyl is going to pick up, it's going to do proton transfer with the acid. So you're going to end up with an intermediate that looks like this. And now that's activated for addition. Right. So once that gets activated, your alcohol is going to come in. I'll just use the one we have. So now this is activated. It's more reactive. That dipole on that carbonyl pi bond is even more polarized towards oxygen because of that plus charge. And so now this can come in and attack here, right? Anytime you add to a pi bond, remember from part one, it's addition, right? You can't do substitution, even though sometimes it might look like a substitution. Like in the end, this is going to look like a substitution. In reality, it's addition followed by elimination, right? So once your alcohol attacks, you're going to get an intermediate that looks like this. All right, let me change the color on alcohol. All right, so my alcohol now is here. That oxygen is positive. And so this intermediate is common to all carbonyl, not this particular intermediate, but this structure is common to all carbonyl additions. This is what we call, and we've seen this already when we did Grignard additions to carbonyls. Right, this tetrahedral intermediate is really common uh, to all carbonyl additions. Like anytime you add to a carbonyl, you're going to go through a tetrahedral intermediate like this, especially if it's like an ester or acid or something like that, that can decompose and reform that pi bond. You'll get something like this, right? So now you got to do a couple of things. First, you want to do proton transfer. So you're going to pick up this proton here. Right, and that's going to set the intermediate up to do elimination. So now you're here. That's positive now. R group doesn't change, and then my alcohol is still here, like that. Make sure I got enough carbons on that. Yes. All right. So now you can eliminate. You can kick off water, and then you end up with the ester, which is here, plus water. All right. And that's this ester. Just to get to the final product, you can just do either proton transfer with the water, or you can do it with the conjugate base from the acid. So let's just say that the conjugate base from the acid is going to come in and rip this proton off. Let's just do it that way. So now you have your ester plus water plus your acid, right? And that acid can go right back and do the same thing again. It can catalyze another addition. So first you have proton transfer here. And again, this mechanism is kind of ubiquitous for these carbonyl addition. So proton transfer, and then you have addition, right? Then you have here elimination. And then here you had a proton transfer also. Right, and these are all reactions that we've already seen before. None of this is anything that we haven't seen. It's just applied to a different example, but we've seen this. And the second reaction with the acid chloride is the exact same. The only difference is you don't need a catalyst, right? So that's even more straightforward. You just attack the acid chloride, you form the tetrahedral intermediate, and then you eliminate and lose chlorine. So over here, let me put that in. That should be let me actually fix this. So there's no water here. It's just it'll be plus HCl. Right, because you're gonna lose chlorine. All right, any questions about that mechanism or that reaction? And again, if you go through it with the acid chloride, the first step is attack of your or addition of your alcohol to that carbonyl, right? So let me just show you because this is a much shorter mechanism. All right, so you have your acid chloride here. And then your alcohol here. That's just going to attack. You're going to get your tetrahedral intermediate. That's negative. Chlorine is here. And then this is O. All right, so that's that intermediate is now going to eliminate and you'll lose chlorine. So you end up with this. That's positive, and then plus Cl minus. And it's just a proton transfer from there. So you'll pull off this proton like so, and then you get your product. This is actually a much more expedient way to get to esters. Those acid chlorides are really, really reactive. Every time I teach this, I always say the same thing about the acid chloride. When you crack the top open on the bottle, it's reacting with the water in the atmosphere. Like it's that reactive. All right, so both of those are going to get you to the same outcome, which is an ester. And again, you can see up here, I started with an acid chloride functional group, and I ended up with an ester in the product. All right, any questions about those two reactions or anything about them?
I have a question.
Go ahead.
So the intermediate would be the same for each of these, right?
Yeah, it's not the it's not the same chemically, but structurally, yes, it's going to be a tetrahedral intermediate. So once you attack that carbonyl carbon, you're going to get an intermediate that looks like that has 4 substituents attached to that carbonyl carbon, which is right here. So that's why we just call it a tetrahedral intermediate. Right, because remember that carbon, it went from sp2 over here is sp2, and over here on the in the intermediate is sp3. So it went from trigonal to tetrahedral because that's the natural geometry for carbon is a tetrahedral geometry. All right. Any other questions? The only other reaction here with this first class of reactions is the ether synthesis, which is right here. And again, I can't stress enough, your prior knowledge of functional groups is critical for this period. I mean, just if you don't know the functional groups, then the reactions are not going to make sense. So if you need to brush up or review or get those old flashcards out or the app or whatever you're using, I highly recommend it. All right, so an ether, which is what we're trying to make here, you can see the ether functional group is here. Right, the basic structure of an ether is an oxygen with a carbon on each side. Doesn't matter what's attached to the carbon. If this is your if this is the basic structure, then that's what we call an ether. All right. And this is another reaction where it's one of those alkyl halide reactions. And we haven't talked about this per se, but we've seen it before because this ether synthesis is nothing more than an SN2 type substitution. Right, that's the type of reaction that is. So when you make ethers, let me make sure I've got all this other stuff out of the way. Right, you always do it with an alcohol. Again, notice all my star materials include an alcohol because that's what we're looking at, reactions of alcohols. That's the class 1 of the reactions that we're going to cover over the next few days. All right, so I got alcohol here and an alkyl halide, and that's it. And I do this in the presence of a base, and we can talk about excuse me, how this happens. So with that base in the presence of that alcohol, let me just show it. All right, so I'm going to take my alcohol here. Alcohols, the proton on an alcohol has a pK around 16, so it is removable by a decent base. Doesn't have to be a super strong base, although sodium hydroxide is pretty strong. So here, all right, all this is acid-base chemistry. So I'm going to pull off that proton like so. Right, and what I'm doing in the process, is making the oxygen more nucleophilic. So sodium will end up hanging out here. So by taking off the proton from the oxygen, I made it more nucleophilic. So now it's a better nucleophile. If you recall from part 1, the rules for nucleophiles, normally if you have a neutral nucleophile, it's less reactive than if you have a negative nucleophile. So this is now a better nucleophile, right? So now that can react with the alkyl halide. So let me just show that step. So I'm just going to redraw it. So let me just give a generic alkyl halide. So here's my nucleophile here. And then let's just say I react this with CH3Cl. Right. All this is again, a SN2 type substitution. This is coming here. Let me write it out. So this is going to give a pair of electrons here and kick off chlorine as the leaving group. Right. Again, nothing new. Everything that you see, we've seen before. And that's going to give me this as my product, O CH3 plus NaCl. Right. And this is my ether. Right. All the stuff that all these arrows and mechanisms, we've seen this already. We know what proton transfer is. We know what a nucleophile is. We know SN2 and how substitution works. I mean, we know all of that. So this is not new. It's just a different application or application to a different problem. And we probably have seen these reactions too when we were working through the substitution stuff. I know for a fact that at least two of the examples we did there were like had an oxygen nucleophile attacking a carbon electrophile. All right, questions about the ether synthesis? All right, so those three reactions are reactions of alcohols. You have, we did ester synthesis either through transesterification or acid chloride esterification. And then we also looked at the ether synthesis, Williamson ether synthesis, very old reaction. I remember learning that was one of the first reactions we learned when I took organic too. So but it's effective because it works. And ethers are very important functional groups in the area of total synthesis when you're making large molecules, especially a lot of your macrolides and a lot of your like natural products that have biological properties. They have a lot of ether linkages in them. All right. Let me add another page. The second class of reactions is we're going to look at alcohol still, but not a different type of reaction. So we're going to look at the oxidation of alcohol. So here it says the conversion of alcohols into carbonyl. So let me take this and cut it out, and then we'll paste it and we'll discuss it. And again, for these reactions, my suggestion, because we're not going to go through each and every mechanism, especially for these oxidations, because the mechanisms get very complicated when you start using transition metals as catalysts. But we are going to talk about what they do. And so here, when we talk about alcohol oxidation, let me see which one we have. Right. When you took GChem, one of the things that you learned in general chemistry about oxidation, well, was that it was the loss of electrons, right? But there's another definition of oxidation that we can kind of attach to that, and it has the same connotation, even though it's a different process, right? So oxidation in GChem was the loss of electrons, right? Like if you went from chromium 2 plus to chromium 3 plus, right? Plus 1 electron. So you lost an electron. And organic, when we think about oxidation, it has really two meanings. And one of them is to increase the number of bonds to oxygen. That's one of the meanings. The other is to decrease the number of bonds to hydrogen. All right, so you increase the number of bonds to oxygen, you decrease the number of bonds to hydrogen. And by the same token, reduction in GChem was the gaining electrons, in organic, reduction is the opposite of oxidation. So it's either decreasing bonds to oxygen or increasing bonds to hydrogen. Let me put that over here. All right, so reduction is the opposite. So all of these oxidations are going to follow a similar pattern. And let me show you. And then we're going to answer a question about oxidation over on the other side. So one of the things that's a prerequisite for oxidation is obviously you need an alcohol. And it can be primary or secondary. We'll make this one, we'll make it secondary. Right? The prerequisite is that you need these two protons right here. Right, so you need those two protons. You need the carbonyl proton, which is here. Right, and you need the hydroxyl proton. If you're trying to oxidize this alcohol up to a carbonyl, you need those two hydrogens there. Right, so whatever you use for your oxidation, it's got to be able to remove both of those protons. Right, so your oxidant or both hydrogens. Right, so somehow you need to lose, and I'm generalizing this because you don't always make H2 as a side product, but you need to get here. So this is your carbonyl plus, let's say, H2, right? So you need to lose H2 in order to get that carbonyl. And that's a prerequisite. If there's no carbonyl proton, then it's really not going to be possible to oxidize that alcohol level. So here you can see this is a secondary right? Secondary alcohol. I'm just going to abbreviate alcohol. If it was a primary, right, you could do the same thing if you had this OH. You can see again, I got those two hydrogens that I can remove, right? But if you have a tertiary, you'll see a problem right away. If this is tertiary, what am I missing here for that tertiary alcohol?
The carbonyl.
Carbonyl. So there's no carbonyl proton, right? You're missing that hydrogen that will be here. So you can't oxidize. Right? You cannot oxidize a tertiary alcohol. You can only oxidize a primary or secondary. And the reasoning is because most of the mechanisms for oxidation of alcohols to carbonyls involve what I just showed you, removal of the carbonyl as well as the hydroxyl proton. So primary is fine, secondary is fine, tertiary you cannot oxidize. All right. Any questions about that? So when we look at the examples over here, all we're really looking at, because we're not going through the mechanism, all we're really looking at are the reagents. Right, so here, if you want to oxidize a primary, again, this is, if you remember when we were doing synthesis of alkyl halides and we had alcohols, and we were saying that if you had a primary, you would use this set of reagents. If you had a secondary, you would use this. If you had tertiary, you use this, so on and so forth. It's the same way when you're doing other types of synthetic methods. Some of them are specific for certain types of functional groups. So if you got a primary alcohol, typically you would use one of these, and there are a bunch of different methods. I'm really paring this all way down just to give us something to grab onto. But typically you would use one of these methods, like what we call Swern oxidation or chromic acid. So let me write this in here as chromic acid or Swern oxidation. Swern uses excuse me, oxalochloride and DMSO as the reagents. And I'm not gonna go through that mechanism because it's pretty drawn out, but I do have a bonus assignment that I'm gonna open up where you can look up the mechanism and then kind of go through it and then upload it. I'll open that up later today. But the Swern is probably one of the stinkiest reactions I've ever done because the reagents involve sulfur. And so at the end, it just smells, the whole lab just smells like rotten eggs. But it's very effective for primary. It actually will work on secondaries too, but primary is really, really effective, really high yielding. Same with chromic acid. But if you want to convert a primary alcohol, which we have here, into a carbonyl, right, an aldehyde in this case, you would use one of these two methods. You would use the Swern oxidation, or you would use chromic acid oxidation. Both of them work, both high yielding, and you're going to get an aldehyde as the product. Notice now, primary alcohols will give me an aldehyde. If I use a secondary alcohol, I get a ketone. Again, the knowledge of your functional groups is critical. You have to know your functional group so you'll see what you're looking at. If you don't know the difference in an aldehyde or ketone, then this makes no sense whatsoever. Right, but if you look right here, this is a secondary alcohol, and over here in the product, I have a ketone. Right, and the set of reagents for secondary that's specific to secondary alcohols is shown right here. It's TPAP, and I'll pull that up in a second. TPAP and NMO. NMO is basically a co-oxidant for this reaction. It helps to get the metal back to its original. Right, so it's like this is NMO and methylmorpholine oxide, and then TPAP is it's a ruthenium catalyst. As a matter of fact, let me just pull it up right quick. I'll just Google it in Safari. But it's a there's a website, organic chemistry portal, and it is phenomenal. Has not every, but it has a ton of reactions and the mechanisms. It's actually this website right here. You can see organic chemistry portal. This thing is amazing. So the ruthenium catalyst is tetrapropyl ammonium perruthenate. So this is the ruthenium part right here, the RU with the 4 oxygens, and then it's the overall, the catalyst is negative, so the oxidation number is -1, and then the counter ion is that tetrapropyl ammonium. So it's ammonia, it's a nitrogen with 4 propyl, so 4 3-carbon chains attached to it. Right, so that is an excellent oxidant for secondary alcohol. So it's TPAP and then NMO because one of the oxygens ends up getting transferred, so you have to reoxidize ruthenium. So that's what the NMO is for. It's a if I'm not mistaken, it's an electron donor to get that ruthenium back to its original oxidation state. Um, so yeah, so TPAP and NMO, that combination, right? You use that for secondary alcohol. I'm not expecting you to know the mechanism. This is a set of reagents that you just need to remember for secondary alcohols is TPAP and NMO. And then if you take primary and potassium permanganate, which is here, this is potassium permanganate. This is what you call a superoxidant. So it will not stop at a aldehyde for primary alcohol. It won't stop. It'll take that primary all the way up to the carboxylic acid, right? So this is, you can see right here, the carboxylic acid here from the primary alcohol. So now you taking that carbon all the way up from the alcohol oxidation state all the way up to the acid oxidation state, right? And that's pretty important because again, these methods are specific. If you need a carboxylic acid, then by all means use potassium permanganate. If you do not need a carboxylic acid, then I wouldn't recommend this if you're trying to oxidize a primary alcohol, because when you do that, it's not going to stop. It's going to oxidize it as far as it can. So these four methods are methods used to oxidize alcohols to carbonyls. If you got a primary and you want an aldehyde, you can use the Swern or you can use the chromic acid. If you have a secondary and you want to oxidize that up to the ketone, then you use something like TPAP and NMO. There are other methods, but this is one of the methods that's routinely used for secondary alcohols. And if you got a primary, you want to make the acid, then you can take that all the way up to the acid using potassium permanganate. Right? That's what you call a superoxidant. It'll keep oxidizing until carbon can't be oxidized any further. All right. Questions about the oxidation, about anything pertaining to oxidation. All right. So we have a few minutes left. I want to show you a couple of examples here. Let's take, yeah, we can do that. Let's take these first two examples right here. So again, when you see, now this is different when you see it in practice, because you have to know that chromic acid is an alcohol oxidant. And the reason I say that, is because sometimes you'll be doing a reaction. Let's say you're doing a synthesis, a total synthesis. There are going to be other functional groups present. So you have to recognize like what reagents are specific to certain functional groups or what functional groups get touched. Because right here, you can see right here, we got three different functional groups. We got an aromatic ring, right? We have an alkene down here, and then we have an alcohol over here. So now we have you see all these different functional groups. It's easy to get confused and say, well, I don't know what's going to happen. You got three things, anything can happen, but that's not true. If you have an oxidant like chromic acid or like potassium permanganate, they're not going to touch the ring. The ring is unreactive without a catalyst, right? If there's no catalyst present to activate the aromatic ring, then it's not going to do anything. The alkene is not susceptible to oxidation under these conditions. So you're not going to touch that. So that's really important to understand when you have, that's one of the reasons why it's good to recognize the reagents, because if you see chromic acid, it should automatically click that this is for the oxidation of alcohols up to carbonyls. The same with potassium permanganate. So with that being said, what is the product of the chromic acid reaction? What am I going to get on the other side of that arrow?
An aldehyde.
An aldehyde, right? And it's going to look like this. Make sure I got that right. I'm going to abbreviate that. That's my product. Notice the ring didn't get touched, nor did the alkene. Right? I took that alcohol and I oxidized it up to an aldehyde. Right? Nothing else got touched. Right? Same thing on the other side. What am I going to get from that? I'm actually going to steal this thing over here.
Carboxylic acid.
Carboxylic acid. So instead of that being a hydrogen, this is not going to be a OH. I know somebody's panicking because this is turned a different way, all that good stuff, but it doesn't matter. That's all semantics, the orientation in space. Actually, it's not turned a different way. So never mind, disregard that. All right. But again, you can see right away the need to be able to recognize the reagents. That's why I recommend making flashcards or using the organic chemistry app that has all the reactions in it, because all of these reagents have specific applications to convert some functional group into something else. All right, let's see if we can pick up on this one. We've done this already. What would the what is that going to act on? Right? I have an alcohol, I have an alkene, I have an aromatic ring, but the alkene and aromatic ring are not susceptible to reaction with sodium hydroxide. Right? That's a base. The alcohol has an acidic proton. So what reaction is that? We just looked at it.
Is it the ether synthesis?
Williamson ether synthesis. That's exactly right. And even if you don't know the mechanism, you can look at the alkyl halide and see what's attached to the halogen, and that'll tell you what's going to be attached to oxygen in your ether. So now that's going to look like this. Let me just fix this up. I'm going to keep stealing it. Right, so that's going to look like this. Well, now this is the CH3 from that alkyl halide. Right, and that's my ether. Again, I know it's not going to click immediately, and I know this is kind of compressed, but some of these reactions, if you recognize the reagents, then it makes it a whole lot easier to remember what's going to happen. All right, we're actually going to stop here. We're going to pick up on Friday. We're going to talk about the Vidic reaction and then hemiacetal formation. And I'm going to send you a video with all this stuff in it sometime this afternoon after my other classes are done. So we're going to stop here.